Here's an example of how we can use the XGBoost algorithm for classification purposes. And specifically in this example, what we're going to be doing is we're going to be working on a hotel data set with the aim of using different features in the data set to predict if a customer will cancel their hotel booking. If we look at this data set in specific, we have the response variable is cancelled, and we have 0 for a non-cancellation, or if a customer goes ahead with their booking, and we have a 1 for a cancellation when a customer decides to cancel their booking. And what we're doing is we're taking these features here, or well, a certain number of them anyway, and we're implementing a boosting mechanism to come up with a classification algorithm to determine whether a customer will cancel their booking or not. And as regards a boosting algorithm specifically, what boosting is it's known as an ensemble method. In other words, what it's doing is it's taking a number of weak learners, such as decision trees, and it's combining those learners in order to form a strong learner. That's why we call boosting an ensemble method. And at its core, what we want to do is we want to build the classification model using this dataset, H1, and then we want to take the response variable in H2 and we want to compare the predictions in the response variable for H2 with the predictions that the model is making. We want to compare the predictions with the actual response. What we'll do then is we'll go ahead and we'll run the code, and things will become more intuitive as we go through this. Firstly, let's import all our variables. Here is the data set that we saw imported into Pandas. The response variable is also imported. And what we're doing is the variables that we saw in the data sets, we are importing these as either interval or categorical variables. Interval means that each variable can take on a range of values. For example, lead time, which is the number of days between when the customer makes their booking and when they're due to actually stay at the hotel. We see this takes on a range of values, and therefore it's known as an interval variable. Whereas others, such as market segment, for example, or country, are categorical variables. They don't take on any particular range of values, they're just categories. We can import interval variables, and then for categorical variables we're using cat codes, and the purpose of using this is to assign a number to each category, but also make sure that Python doesn't treat those categories in ranked order. For example, if we go back to our data set here, let's take the example of countries. We have bookings from Portugal, Great Britain, USA, Spain, Ireland, etc. But when we assign a number to each of these countries, we don't want a situation where Python is treating it in ranking and therefore ranks certain countries above others. We just want independent categories in their own right, and for that reason we're using cat codes. The response variable is imported, and we import a select few features as a NumPy stack. I'm not going to go through why specifically we choose these features. That's a separate discussion on feature selection, but I will link to a source regarding that if you wish to get more information as to why we're choosing those. This is our response variable. This is our NumPy stack. We are then splitting the data into training and validation. The training data is what we use to build the boosting model, and then the validation data is what we use to validate the predictions against our actual values in the validation set, and the model then can recalibrate accordingly. Now, When we run our XGBoost algorithm, we're going to be using what's called a confusion matrix to assess the accuracy of this algorithm. Now, before we get into accuracy, what we need to be cognizant of is this idea of precision versus recall. Now, precision versus recall can be influenced by the false positives versus false negatives in a particular data set, or the results that a particular model is giving us. And what we need to be cognizant of is that in this data set here, we have many more zeros than we do ones. In other words, there are many more customers who will book with a hotel but then follow through with that booking, as opposed to customers that will cancel. And as a result, we have an unbalanced class, and this is going to skew our model. As a result, what we want to do is we want to increase the scale weight in the XGBoost algorithm. Here we've set it to 3, and we're going to experiment with this and you'll see how it works. But essentially what we want to do is we want to penalize errors on the minor class to a greater extent than on the major class. In other words, if the predictions regarding the customers who are a 1, the customers who actually cancel, if those predictions are wrong, then the model will penalize errors on those predictions to a greater extent than they will on the 0 class, or the customers who actually follow through with the booking. Let's go ahead and run the XGBoost algorithm, see what we come up with. Now we have an accuracy of 57% on the training set, 57% on the validation set. We'll go ahead and run our predictions. Now, we see here that our accuracy reading on the F1 score overall is 57%. Now, the reason the accuracy is not as high as we'd like it to be is because we have many false positives in our data. But note that when we look at recall, we have an accuracy on the positive class of 93%. And the reason that that's happening is because since the model is tolerating more false positives than false negatives, it means that more of the customers are being classed as a cancellation risk. Now, to explain this more clearly, we need to go back to this idea of precision versus recall. Supposing I'm a doctor, which I'm not, but supposing I tell a patient they don't have cancer when they actually do. That is a false negative, and the consequences of that are a lot more severe than a false positive, telling somebody they do have cancer when they actually don't. And this precision versus recall balance can depend on the situation. For example, if we take the issue of spam emails, we would rather have false negatives than false positives. For example, we would rather a spam email came into our inbox and it was erroneous, rather than having an important email go into the spam folder. So in taking the example of the doctor versus the example of the spam email, we see that false positives and false negatives have differing levels of desirability depending on the situation we're looking at. Now, as regards this specific example, while we wouldn't want to have too many false positives because that defeats the purpose of our model, we would like to have a certain number of false positives because the hotel manager would rather say, okay, I know that a certain number of customers are going to cancel their booking. I would like to be a bit more cautious, and I would like to assume that more people will cancel than actually will, and as a result I can then glean or find out the features or the attributes that are common to those customers that actually end up cancelling their booking. Now, these results that we've come up with here are results on the validation set. Now, what we want to do is come up with results for the test set. We want to take the predictions, or we want to take the model that we built using the first data set, and we want to use the data from the second data set to feed into that model and ultimately come up with predictions for the second data set. Let's go ahead and run this here. Again, we're importing the interval and categorical variables and just running the usual data manipulation procedures. And let's see what our confusion matrix looks like here. We have an accuracy of 55% and we have a recall of 94%. So the recall was slightly higher for the test set than it was for the validation set. And as I mentioned, in this instance, the hotel would likely like to see more false positives than false negatives because they want to get more information on the profile of the customer who is likely to cancel their hotel booking, and then they can adjust their marketing strategies to target different customers accordingly. Now, what I'm going to do is I'm going to reset this and we're going to manipulate this model a little bit. Let's go back to the weight. We set it here to 3. Now, the higher we set this weight, the more the model is going to penalize errors on the minor class. But let's say we set this back to 1. What I'm going to do is run this data set once again, this notebook rather, once again, and we'll see what we come up with. Now, I'm just going to go down to the test set here because that's the litmus test of what's important. We can see now that our F1 score has increased to 74%, but observe that the recall score for class 1 has actually decreased to 39%. And what this basically means is that we're getting less false positives for our model. So the overall accuracy is increasing, but it means that the model is detecting less of the customers who cancel. So for example, of all the customers who end up cancelling their booking, this XGBoost model is only detecting 39% of those, which from that standpoint, the model is not doing what the hotel manager would like it to do. Let's reset once again, and this time let's take the opposite scenario. Let's suppose we give a very high weighting to the scale weight. We'll run this again, we'll see what happens. Now, we have a perfect recall of 100% of all the customers who cancel their booking. This model detects 100% of them, but the accuracy overall has fallen further to 44%. Now, even though false positives are better than false negatives in this instance, it does come with a limit, because if we continue setting the weight higher and higher, if we continue setting this higher and higher, eventually we're going to get to a point where all of the predictions are being flagged as false positives, and that doesn't really do anything for the end user, because it's not explaining, it's not allowing the end user to distinguish between the characteristics of customers who do cancel their booking versus those that don't. To recap, when we're running the boosting algorithm, we are taking into account not just the overall accuracy metric, but the precision versus recall, and we're then using a confusion matrix to assess whether we are getting a good blend of overall accuracy, but also whether we have a high precision or a recall that we want, depending on the circumstances. And in this particular case, the original weighting of 3, when I ran this, I found that to be the best weighting to maximize recall, but also have 55% accuracy. It isn't great overall, but for this particular case, for this particular instance, we want to maximize recall to a reasonable degree, because we want to find out the profiles of customers who are likely to cancel their booking versus those that are not, and distinguish on the attributes between them. That's an introduction to the XGBoost method. Hope you've enjoyed this tutorial, and if you have any questions, please leave any comments and I'll answer them as quickly as possible. Thank you.